Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture number 25 in the course Advanced Robotics. In the last class, we looked at the concept of series elastic actuators, where we have a stiffness element like a torsion spring introduced in between the motor and the link. The advantage of that is if there is a sudden impact or a force coming on the link, then that impact will be absorbed in the spring by means of a deformation and it doesn't get transmitted straight onto the motor. Okay. But we also saw that if you do that, then what happens is that you have added a passive element which you cannot directly control. So depending on whether you're taking the feedback from the link side or the motor side, the system can start becoming unstable. Okay, so today we'll very briefly revise what we were doing in the last class, and then we'll move on to the next topic, which is force control in constrained tasks. So whatever we have been doing till now, with the exception of the series elastic actuator probably, is that the robot is moving in space. The end effector is free to move in space and it is not constrained. For example, it is not hitting an object or not touching anything. Okay, so there is no force which is coming on the end effector. So in force control in constrained tasks, for example, if you're doing a grinding operation, so with the hand you're holding a grinding wheel, okay, with the robot end effector, and the grinding wheel has to be pressed against the wall and it has to be moved in a particular direction. So you need both position control in a particular direction and you need force control in another direction. So this question comes up that can you control forces? When can you control force? When can you control position? Can you control force and position simultaneously? For example, if I say that you apply 10 newtons at this point, so we have this point in free air, and I say you apply 10 newtons. Can you apply? No, you cannot apply. Why? Because there is no reaction force. This is air, so you can't apply 10 newtons there. If you try and apply, what will happen? You'll just keep moving that. Whereas if I have a constrained environment like this phone, for example, and it is constrained, in that case, if I say at this point you apply 10 newtons now you can apply. Why? Because this surface, assuming this to be a rigid surface, is going to have an opposite and equal reaction. So when I'm pressing in this direction, there is a reaction in that direction. So now I can apply 10 newtons in this direction. Okay, but I cannot move in this direction. Now suppose I say you apply 10 newton at this point and you move with 1 meter per second in this direction. That you cannot do. Why? Because it is constrained. Okay, constraint means there is a rigid object which is not allowing it to move. Okay, but I can apply 10 newton in this direction, but I can move in this direction. Okay, now you see the direction of the force and the direction of the velocity are orthogonal to each other. Okay, so this is basically what we are trying to look at in today's class. That is, when you're applying forces in constrained tasks, how do you control forces in constrained applications of constrained task performance? Okay, we are looking at force control in constrained tasks, and we are trying to explain what is the meaning of the word constrained task. It basically means that we are trying to apply force in a particular direction which is opposing the force. So there is a equal and opposite reaction. Now before going there, we'll just revise very quickly what we had done in the last class. In the last class, we talked about series elastic actuators, or what we call drivetrain dynamics, in which case in the drivetrain itself, okay, so this is my motor and on the other side we have the link, and in between the motor and the link there is a stiffness element which is your spring here. Okay, in the normal case where there is a gear, this is a rigid element, so there is no deformation. So whatever is the theta m here, it will be reduced by the gear ratio. Okay, so theta m by r, and it will become theta L. Okay, so there is no loss in between, or there is no deformation in between. Whereas in this particular case, as shown here, there is an element in there, a torsion spring. So if I rotate this by some angle, let's say theta L, sorry, this is the motor side, so theta M, this is my theta L. Now theta L will not be equal to theta M because there is some the spring is going to deform and it is going to absorb some of your rotation from the motor side. Advantage of this, if I have a force or an impact load coming in there, part of the force is going to be absorbed in a deformation here, so it will not get transmitted onto the motor side. Okay, in terms of safety, in terms of mainly in terms of safety. Okay. So today we talk of safe robotics, a lot of robots where this kind of series elastic actuators are used. Now, what does it physically mean? In the last class, I couldn't play the video. Hopefully, this class will be able to play the video and show what it basically means. So it basically means that if you have a link, which is shown here, so this is my link and there is a torsion spring in there, okay? In the center, we can say that there is a torsion spring. Now, depending on how stiff or how hard or how high the value of K is, it will move easily or it will not move easily. Okay, let us go back and have a look at this one more time. Let me just go back and let me just explain this. So we have a element like this. Let me call this a link, and it is mounted on a revolute joint about this axis. That's a revolute joint, and there's a torsion spring there. Torsion spring is connected to the link like this. Okay. Now this spring has a particular K of stiffness. Now if it is very stiff or it is less stiff will depend on how this is going to behave. So if I give a force here, okay, if K is low, then what will happen? This will rotate a lot, okay, because F is equal to K into del theta. So if K is small, what will happen is this will tend to deflect a lot. If K is very high, it will deflect very less. Okay, so that is the way we are going to defend, we are going to say, or how K determines the behavior of this link. That is what this video is showing, that when the person is pushing, for example, okay, the person is pushing, and we are trying to show the concept of variable stiffness. So the person is applying a force. This is virtual spring rate, high virtual spring rate. This is low virtual spring rate. So everything depends on the value of K now. Okay, this is a high virtual spring again. This is a low virtual spring. Okay, in case of impact, this is most, if you hit it, there's an impact, but this K value is pretty high. Okay, whereas in this case, there is a low virtual spring rate or a low K value. So it is going to behave in the way that you're going to, that depends on the value of the K of the spring now. So in an adaptive kind of a system, we can actually vary the value of K. So this is my K, the stiffness of the spring. I can vary this K and I can make it behave in a particular way, just as it was being seen in the video. Okay, so this is just to give you a physical understanding of if you vary K, what happens. Okay, in the last class, we saw that when we have a drivetrain dynamics of this nature, where we have a motor on one side and we have the link on the other end, and there is a spring in between. Please note that this spring is a passive spring. Okay, and writing our torque equations from the link side. So this is my link side torque, this is my tau L on this side, and this is my tau M on this side, on the motor side. Now when we write our equations from the link side, we have this equation, and on the link side, because this K is passive, you cannot control it, there is no control input there. Okay, whereas when I'm looking from the motor side, this is my inertia, this is my damping, and this is my minus K into theta L minus theta M. So this is my theta M on this side, and theta L is on that side. So effectively the difference between this and this is going to be K into, so F is equal to K into theta L minus theta M. Okay, and here the motor is giving the input, so I'm having my input U. In terms of control system block diagram, we draw it like this. Okay, so from these two equations, from this equation and this equation, we write our block diagram this way. We draw our block diagrams this way. Now, when I find the transfer function, we see that our transfer function is theta L by US, which is equal to K by PL PM minus K squared, which is this term. So the denominator of that is my characteristic equation, and I need to look at the roots of that equation to talk about stability. Okay, so if you look at if I expand the equation, then what we get is, putting in all the terms, is this. Now we can say that BM and BL are very small, so BM is equal to BL, which is damping is small, is equal to 0, so I end up with S raised to 4. So this becomes S squared into JM, JL JM S squared plus K into JL plus JM. Okay, so now if I put this equal to 0 to find the roots, we'll have two roots at the origin, and we'll have we'll have a pair of complex conjugate roots. Now this means that all the roots are negative, so roots are negative or 0, and hence this is a stable system. Okay, so this system is stable. Now as a system it is stable. Now if I add a PD controller, I'm going to control the system using a PD compensator now. So this is my PD controller. Now if I add the PD controller, I have two options. One option is to take the feedback from the motor side or to take the feedback from the link side. Okay, so in this case it basically means that if I have an encoder, I place the encoder here, this is my encoder, and take the feedback from here. Or I place my encoder on this side, on the link side, and take the feedback from there. I have two options now. Okay, and the readings of these two encoders would be different. Why? Because there is a spring in between which is getting deformed. Okay, so depending on which side you take the feedback from, if I take the feedback from the motor side, this is taking the feedback from the motor side just after the motor output. This is my feedback, okay, which is coming here and here. In that case, if I draw the root locus, we find that all the root locus stays on the left side of the j omega axis, which means that this is a stable system. So for all values of kd and kp, this system is stable. Okay. Whereas if I take the feedback from the link side, this is my link side, PL is the link side. So on this side, if I take the feedback, then what we see is that the root locus, after a particular limiting case, what happens, it goes to the right of the j omega axis, and this basically means that this can become unstable. This is unstable. Okay, so this means that there are critical values of kd after which the system will become unstable. Okay, so we should be very careful that when we are doing this kind of control of series elastic actuators, or when we are putting a stiffness element in between the actuator and the link, then we have to be very careful that which side we are taking the feedback from, and we have to ensure that it does not become unstable. Okay, now this is just to revise. Let's move on to today's topic, which is force control in constraint tasks. Okay, so when we're talking about force control in constraint tasks, an example I just gave some time back is that you're having a robot which is doing grinding. So this is a grinding wheel which is rotating like that, and this is a wall which it is polishing, for example. Okay, so this is the grinding wheel is rotating. So the robot has to apply a force in this direction to maintain contact at that point. So there has to be contact here, right, to do grinding, and as it is grinding, the wheel has to be moved in this direction. So there is a velocity in that direction and there is a force in this direction, and both of these are orthogonal. Okay, now when we talk about, you can look at different examples. For example, peg in the hole assembly. So for example, if we are trying to assemble a part inside a hole, you can think about this as a pen and a cap. So you have a cap of the pen and you're trying to insert it. Now this is what we call the peg in the hole assembly. So this is called a peg and this is called the hole, and we are trying to assemble this automatically by a robot. Okay, so that's my peg. So the robot is expected to hold this. So the robot, if you can imagine, the robot end effector will hold this with the two fingers. So this is the robot end effector with two fingers. It will hold this, and then the robot will try and assemble this peg inside here. Now this is a constraint task. Why? Because in some directions it can move and some directions it cannot move. You can imagine this, right? So when you're putting a pen, so if I say that this is my cap, this is a pen, you can imagine that this is a pen, and this is the nib of the pen. Okay, let's say it's a ballpoint pen like this, and I'm inserting, okay, the cap onto the pen. This is almost similar to this peg in the hole assembly. So in a particular direction it can move, it is free to move in this direction, it cannot move in that direction. Once you insert, there will be some constraints which are coming. Another example I can give is you are holding an object. Let's say you're holding a cube using a multi-finger robot hand. So we'll also look at multi-finger robot hands just after this. So suppose I have three-finger hand. So this is index finger, middle finger, and the other side is the thumb, okay, on that side. And this is my multi-finger hand. I'm holding this cube. So I'm grasping the cube and I'm manipulating the cube, doing two things. Okay, so I'm doing these two applications using this multi-fingered hand. Now if I draw another view of this object, so this is my fingers, if you can imagine, this is my fingers, and this is the side of the thumb. Okay, so when it is in free space, the fingers are free to move. Okay, so there is free motion in space when there is no contact. The moment contact is made, this gets constrained, so it cannot move in this direction anymore because it is constrained there. Okay, but it can apply a force. So this question of force and position or position depends on the task, depends on which direction you can move, which direction you cannot move. Okay, and it has to be controlled accurately in order to perform a task. And this is what makes robotic assembly very, very difficult. Okay, now let's try to understand why. Because there are what we call natural and artificial constraints. Okay. What are these natural and artificial constraints? This basically means that when you are performing a particular task, there are some natural constraints which are being put on the task. Okay, let's take an example. Suppose I have a wall. Okay, so on this wall, I have an end effector which is holding a tool. So this is my robot end effector, okay, which is holding, let's say a particular tool, okay, like this. Now, because there is a wall here, there is a natural constraint. What is the natural constraint? It will not allow you to move in that direction. So velocity, if this is my x direction, if this is my x direction, that's my y direction, then Vx will become equal to 0. Okay. So this is a natural constraint. It is not allowing you to move in that direction. Okay. And there would be some artificial constraints also. For example, in this particular case, suppose I want to press in this direction, I must make the velocity in that direction Vy to be equal to 0. That's an artificial constraint. Okay. Otherwise, what will happen is if I allow Vx and if I allow a force and I apply Vy, then it will not apply here. It will start applying a force here and start moving in that direction also, like the case of the grinding wheel, which we don't want. Okay. So if I explain the same thing here, suppose I want to apply the grinding wheel only at this point. I don't want this fellow to move. Okay. V dot x is equal to 0. Okay. So in that case, I have to make V dot x equal to 0. Otherwise, it can start moving in this direction. So this would be an artificial constraint, and there would be natural constraints because of the wall. So the wall is putting a natural constraint. This is a natural constraint which is being put. Okay. And I don't want to move in this direction. That's an artificial constraint, depending on what I want to do. Okay. Let me take an example here. Let me take this example of peg in hole assembly again before we proceed. Okay. So this is my peg in hole assembly. I want to insert this peg inside this hole. Okay. So this is my peg which I'm going to insert into this hole. Okay. Let's say this is my x-axis, that's my y-axis, and there can be a z-axis on this side also. Okay. Or let me just say x, y, z, x, y, and z-axis here. Okay. So now if you can imagine, if I draw the top view of this, okay, I'm drawing the top view. Okay, and there is a hole in there. Okay, that's the hole where I want to insert it. So the robot cannot, or rather the robot can only insert the peg in this direction, Okay, so it can have a velocity in that direction only. It cannot have a velocity in another direction. The moment the peg is inserted a little bit, it cannot have velocities in that direction. So y dash must be equal to 0. That is a natural constraint now. Okay. Now when it is inserting, we should not rotate it like that. So that is a omega, let's say omega z is equal to 0. I have to maintain this, becomes an artificial constraint. This is a natural constraint. So when the peg is here, if you can imagine that, let's say this is my peg. Okay, this is the peg, and I want to insert this into that hole. So the robot is holding this peg, and what it can do is it can try and approach the hole. So it has to have a velocity in that direction. Here it cannot force it down. So Fz must be equal to 0 because it can't force it through here. Okay, sorry, Fz will not be 0, but the velocity in this direction, so Vz will be equal to 0, which is a natural constraint. So it cannot force the peg into this surface because there is no hole there. Only when it approaches the hole and reaches the hole, exactly fits the peg inside there, then it can have that velocity. Otherwise it cannot. Similarly, when it has been inserted here in the top view, it has been inserted, so contact is made there. Now the moment contact is made there, you cannot move it in this direction anymore. That velocity is gone. So in this case, please note, I could move the peg in this direction or this direction. That means x dot and y dot was possible. Okay, but z dot was not possible. Z dot was equal to 0. So these are natural constraints. Whereas the moment the peg is exactly fitted onto there, in that case I can move it down, and once I move it down a little bit, it has entered the hole. This velocity will become 0 there now. So x dot and y dot will become 0 because you can't move in that direction. Now while doing the task, you may not want to rotate it about that axis. So the angular velocity has to be maintained as 0. Okay, so this means that given a task like this or like this, there are some natural constraints and some artificial constraints which are set up. Natural constraints are because of the system itself. Okay, that there's nothing you can do about it. Artificial constraints are the ones that you have to control. So to perform the task, you have to control the artificial constraints. For example, I can just give you an example that after you move the peg on this table such that you align the peg with the hole. The moment it is aligned, then you move it down. Okay. So for example, the task here could be that have a particular velocity x dot in some direction or y dot in some direction. The peg is here. Okay. So I'm moving it with some velocity v. Okay. So I'm moving it in this direction until this peg is aligned with the hole. Once it is aligned, then I move it down with a velocity in the z direction. Z is equal to vz. Okay, so this is the way I should be able to perform the task. But when I'm doing this and this, there will be other constraints, natural and artificial, which I have to maintain, which I have to control. And this is what makes force control very, very difficult. Okay, so let's look at this example, which will probably clarify the matter a little bit more. So this is turning a crank or a handle. So let us say this is turning a crank or handle. Okay, so this basically means that I'm going to turn this crank or handle. So this is the robot end effector or gripper. It's holding it here. That's my end effector. Okay, so this is my robot end effector which is holding that. Okay, now this is my local axis x, y and z. Please note this is my x-axis, y-axis and z-axis. Now what is the objective? The objective is, this is the crank. I want to rotate it like that. How do I rotate it? I catch it here and then I apply a force in that direction. Okay, now if I apply a force, what is happening? There's a moment which is coming about this axis and then this is rotating like that. Okay, I hope you can imagine this. Please imagine this first. Okay, that how am I going to turn this handle? I will hold it here and then I'm going to apply a force in that direction. Okay, now what would happen is, because of this itself, there would be natural constraints and artificial constraints. So there will be natural constraints and artificial constraints. What are the natural constraints? The moment you hold it there, okay, you put your finger, when you hold it, there are two grippers on two sides. Okay, you're holding it there. Okay, now what are the natural constraints that have automatically come into picture? So Vx will be equal to 0. That is my x direction. So the moment you're holding, you cannot move it in this direction, right? Because it is constrained there. Okay, so Vx is equal to 0. Then Vz is equal to 0. You cannot move in the z direction because you're holding it there. Then omega x is equal to 0. So you cannot have an angular velocity about that axis. Okay, you cannot do that. And omega y is equal to 0. Okay, and what about in terms of force? You cannot apply a force in this direction. Fy is equal to 0. If the moment I apply a force in this direction, what will happen? It will move. So if it is moving, you cannot apply a force. I was just giving the example that in free air, you cannot apply force because there is no reaction. Here there is no reaction. The moment you apply a force, this handle will rotate. So Fy is equal to 0 and the moment Nz is equal to 0. Okay, the moment about the z axis is also equal to 0 because it will start moving about that axis if you start applying that moment. Okay, so now what we see is that, let me just go back and explain. From these examples, we understood that there are natural constraints and artificial constraints, and you have to control the artificial constraints in order to perform the task. Now, let us ask the question that how many are there? Okay, so we know that there are forces, there is linear velocities, there is angular velocities, there is moment, there is forces, and there is moments. Okay, I can say n is moment. Okay, how many linear velocities? Vx, vy, vz. How many angular velocities? Omega x, omega y, omega z. How many forces? Fx, fy, fz. And moments nx, ny, and nz. So how many are there? 12 are there actually. Okay, that means you actually have to, some of this will be natural, some of this will be artificial. What are natural constraints? You cannot do anything about it. Whatever are artificial constraints, you have to control them. So it basically means that if I simply say that the robot has to do a particular task, it is not doing one particular task could be made up of several artificial constraints that need to be controlled, as given here. These are natural constraints, so we don't need to do anything about them. What about the artificial constraints? Okay, the artificial constraints are in order to move, you must have a particular velocity. Vy is equal to alpha 1. Okay, so in order to perform this task, I want to rotate about this axis. So I'm going to use a velocity here. Okay, that is my Vy. So I have to give a control velocity to move in a particular direction, and omega z must be equal to alpha 1. This is r into alpha 1. This is r. Okay, so that's my r. Okay, so this is an artificial constraint. What about in terms of fx, fy? Now fx has to be 0 because I should not apply a force in the x direction. Fz must be equal to 0, and nx must be equal to 0, and ny must be equal to 0. If you add this and this, there are 12 actually. This need not be controlled. So this part needs not be controlled. Okay, because they're natural constraints. These fellows have to be controlled. So you see that a simple task of rotating this crank about this axis actually means that you have to control how many variables. There are 4 and 2, 6. You have to control 6 parameters. Okay, you have to control this velocity, angular velocity, linear velocity, fx, fy should be 0, 0, nx and y should be 0, 0. Total is 12. That means to perform this task, you actually have to control these 6 variables now, and that makes it difficult. Okay, so it is not like you can control only one variable and do a task. It's not like that, because there are 12 variables, some of which are natural, some of which are artificial. You have to control the artificial variables because the natural variables are automatically controlled. You don't need to control them. Okay, let's look at another example. This is another example, turning a screwdriver. Okay, so this is turning this is something you would be very familiar with. Okay, turning a screwdriver. Now you might have experienced this by yourself also, that when you, how would you tighten the screw? You put the screwdriver head, so there is a head on the screw, so you insert the head of the screwdriver tip into the head of the screw, and then you rotate. Okay, so I'm going to rotate about that axis in order to tighten the screw, and in the reverse direction to unscrew the screw. So the first thing that we need to do is to apply to put a local axis. So I put my XYZ axis. Please note X, Y, and Z axis. Okay. Then I have to find out what are the natural constraints. Okay. Now in this task, what are the natural constraints? When you have inserted the screwdriver head into that slot, there would be a slot in there, right? So there will be a slot in which the head is going inside. Once you're doing that, you cannot move the screwdriver head in this direction because it has gone inside the slot. That means I have a natural constraint Vx is equal to 0. Okay, because I cannot have a linear velocity of the head in the x direction because it is inserted into the slot on the screw. Similarly, I cannot have an angular velocity omega x is equal to 0, omega y is equal to 0, and Vz is equal to 0. In terms of forces, Fy is equal to 0 and Nz is equal to 0. Please think about the natural constraints. It is pretty easy to understand that you cannot have this screwdriver head cannot have a velocity in that direction. Similarly, it cannot have an angular velocity like this. Okay, because if you have an angular velocity, this contact here will break. Okay, the screw driver will become like this now. Okay, so you cannot have an angular velocity about the x-axis. Similarly, you cannot have an angular velocity about the y-axis. You cannot do like that. Okay, and you cannot have a linear velocity in the z direction. Y is constrained, so you cannot have a velocity in that direction. Okay, so these are the natural constraints. If y is equal to 0, in this direction you cannot apply a force because it will move and come out. Similarly, nz is also 0 because if I try to rotate like that, it will rotate, so I cannot control the force there. What are the artificial constraints? The artificial constraints, first of all, is because the screwdriver head can move in this direction. Okay, so I need to ensure that there is no velocity in that direction, otherwise the contact will break. Okay, the screwdriver head will move off this side and the screw will not get tightened. Wz, there has to be angular velocity about the z-axis. which is my WZ. So when you're rotating the screw clockwise, anti-clockwise, let's say like this, okay, to tighten it or unscrew it, you have to control that omega Z about the Z axis. Similarly, there is Fx is equal to 0. We should not apply a force in the x direction. Nx is equal to 0. Ny is equal to 0. And Fz, we should apply a small force, which is alpha 3. These are my artificial constraints. So I need to keep the head of the screwdriver and the screw in contact. So I have to apply a small force there. So this small force can be called. So I'm sure you would have experienced this, or if you have never experienced this, then please try tightening a screw and see. So what you have to do when you're tightening a screw is you have to take the screwdriver head, insert it into the slot. So there is a slot here on the screw. Okay, insert it there. Apply a small force in this direction and then have an angular velocity in that direction. So basically you're doing this and this only, but then there are other constraints which have to be controlled, and total of them are 12. Okay, this is why a robot would find this extremely difficult, if not impossible to do, because it is not that you are controlling only one angular velocity, you are controlling 4 plus 2, 6 variables here. Okay, and controlling 6 variables is extremely complicated. So no robot will probably be able to do this. Okay, so this looks very easy, but it's not, because of this large number of constraints which are involved. So what we are trying to see here is that whenever there is force control in constraint tasks, this becomes very difficult for the robot. Okay, now let's look at another example. The example is grasping. Okay. So you have a multi-finger robot hand, 2-finger or multi-finger, which is trying to catch an object. So the example I just gave some time back is that I have a cube like this, and we have a multi-finger robot hand, 3 fingers maybe, and 3-finger hand is capturing this like this. Okay, this is on the other side. Okay, it is okay. Now, how would you catch an object? Suppose we have an object kept on the table. This is my table, and there is an object in there. Okay, and I want to catch this object. Okay, so with a gripper, for example. So I'll bring my gripper. So the gripper is coming like this, and the gripper will be positioned like this. Okay, and then what will I do? I'm going to close the fingers. Now the moment you're closing the fingers, this is in free, it is not in constraint task anymore. That means the fingertip is free to move. In that case, you can have position control. What we talked about in terms of PD or PID control, these are position controls methods, and they are for free motion only. Okay, now as I'm closing the hand, the fingers, what is happening is it will become like this, and then it will make contact with the object. Okay. Similarly here, the finger is making contact there. The moment contact is made, you are not in free motion anymore. You cannot move in that direction. Okay, that velocity will become 0. Okay. Similarly here, you cannot close. Once you have made contact with the object, you cannot close anymore. So the velocity in that direction becomes 0. Okay. So this is free motion. And the moment you're in constrained motion, then you start doing force control. So once contact has been made, now you can apply a force there to catch the object. Then you catch it and then move upwards. Similarly here, when you're catching an object, after contact has been made, you can apply a force F, by which you can actually grasp the object. So when we say grasping, we basically mean applying a force at the fingertips and catching the object. Okay. So if I say in steps, what were the 2 steps involved? Number 1 was free motion with no force. Okay, and the second was no motion with force. Okay, so you see it is force or position, not force and position. If you're saying force and position control, these have to be orthogonal to each other, like in the case of grinding. But if you're trying to apply force and position control in the same direction, you cannot do it, because it's a constraint task. So it's force or position, and such controllers which operate like this are called hybrid controllers. They are sometimes also called force position controllers. Force position control. Okay. Now, this means that there is a position controller. So this is my position control law, which can be a PD controller or can be a PID controller. This is in free motion, or when the fingertip or the robot end effector is free to move. The moment, so the fingers are closing using this control. So our input is acceleration, velocity, and position. So if I can take the example of the capture of the object, okay, using a 3-finger hand. So these are the 3 fingers which are there. There's 1 finger here, and there is the thumb finger on the other side. Okay, so when it is in free motion, then we are using position control. The moment contact is being made, okay, the moment contact has been made, we switch to force control. Okay, so there we are controlling force, and it is force or position. Please note that it is or, it is not force and position. You cannot control force and position in the same direction. Okay, so these kind of controllers are called hybrid controllers or force position controllers, where you are either in position domain or in force domain, and in between there is sometimes instability. Okay, you can understand that if the force is not enough, the object can fall this way, it can slip. So that is an unstable phase. Okay, but such position controllers, or rather such controllers, are called hybrid controllers, where you are controlling the force or the position to do a particular task. Examples, similar example can be given in the case of suppose I am having a robot here, okay, which is holding a tool at the end effector, and it is pressing against a wall. So this is my end effector, and it is pressing against a wall. Okay, I want to apply a force F in that direction, and okay, now here also, when contact has not been made, you can have a velocity in that direction, x dot equal to something. Okay, the moment so it can be under position control. The moment contact has been made, you switch from position control to force control. Okay, so this is also an example of a hybrid control, where you are switching from between force controls and position controls. Okay, now there is another class of robots where robots are supposed to be interacting with humans. This is a constraint, okay, or a rigid constraint. Now suppose there is a robot and a human doing a task together, then what? Okay, so this is one extreme case where the constraint is rigid, a rigid wall where it will not allow you to move in that direction. The other is, suppose there is a human who is holding okay, so this is a human who is holding an object, let's say is holding an object, and there is a robot on the other side. So there is a robot on this side, and let me say there is an object which is being held. This is an object, and there is a robot on the other side who is holding this object with the robot gripper. Okay, so this is a robot multi-link robot manipulator, which is okay. Now the robot and the human are holding this object, so this is almost like, this is not free motion anymore. Okay, this is constraint. Here we sometimes have the concept of the what we call impedance control. Okay, now we also have the concept of leader follower. This can be the leader, that can be the follower. So the human applies the force F, the robot senses the force F, and then moves by a distance x. Okay, so what we're trying to find is a relation between force and position, and this is sometimes called an impedance. Okay, so this is another example which is constrained motion, in a way that when the human is pushing or pulling, the robot is also having to follow the motion, and it's not a rigid environment contact, but the environment itself is changing. Okay, so this is a new kind of robot which are called cooperative robots. So these are in the industrial robots. In industrial robots, basically, this is something which we talk about as industrial robots. Industrial robots, you will find that the robots are kept inside a cage. So there is a cage, and there is no interaction between the robot and a human. There is no human anywhere inside the cage for safety reasons. Okay, so this is an industrial robot, strictly industrial. Now, in the case of cooperative robotics, as I was just explaining, for example, there is a robot and a human who is using the saw to cut wood. So the robot and the human are in the same workspace, and they are cooperating. So these are cooperation between the robot and the human to do a particular task. Okay, so these are cooperative robots, or what we call, sometimes also called cobots. Okay, collaborative robots or cobots. Now in this case, we have a robot on one side and you have a human on the other side, and there is some exchange of information between the robot and the human. This information exchange between the robot and the human may be in terms of flow of forces, can be motion, can be gestures, can be EMG, EEG, speech signals. For example, the human could be telling the robot move back, okay, with a velocity of 1 meter per second. That is information exchange between the robot and the human. Or there could be a force sensor which is there at the wrist, so that when the human is pushing with the force F, it is sensing that force F and then moving in that direction. Okay, so there is some information exchange which is going on between the robot and the human. Okay, and in terms of design of such controllers, we talk about this as robot-human interaction control systems. So we have the human control system. This is the human control system. This is the human body. So we have the brain. Now let's look at the example of this. Okay, when I'm trying to explain the control system. So there is the person who is sawing. So he has a brain, and from the brain he thinks, and the signal goes to the muscles, and the arm moves. So the person thinks to move in this direction or that direction. Okay, so the person is thinking using the brain. From the brain, the signals go to the muscles actuate, and a force is developed at the end effector, the arms. It applies a force on this, and then the hand moves. The musculoskeletal system, which is the arm moves. There is a feedback. The person can feel that his arms are moving, and he can also see that the arms are moving back. So there is a feedback control loop which is going on. So this is the human control system. Now on the other side, there is a robot. Okay, and the robot is also feeling the force by means of a force sensor, and then the robot also has to behave or follow the motion. Okay, so the robot control system is here now. So the robot feels the force, either force sensor. It can also use EMG, EEG to look at the force. Then there's a robot controller, which can be PD or PID, and based on the control action, it actuates the actuator and it follows the human. Okay, so this is also called leader follower kind of structure. Okay, so this is different in the sense from an industrial robot, that we have a robot and a human who are doing a task together now. Okay, so this is another example where there is a human and a robot who is performing a task, and here we need to discuss about two terms that are used. One is called admittance and the other is called impedance. Now you might think that what is so difficult about this? Okay, one thing which is very difficult in terms of force control is that in constraint tasks, okay, you are not only going to control one parameter or one variable, you have to control actually 12 variables, some of which are natural constraints, some of which are artificial constraints. Okay, so here we saw that in terms of the variables, a very simple thing like turning a screwdriver, very simple example. Now what is so difficult about this? But in order to perform this, there are natural constraints, there are 6 of them here, and there are artificial constraints, another 6, and the 6 constraints have to be controlled. Okay, that means to perform this task, the robot should be able to control the 6 constraints. Otherwise, it cannot perform this task. Okay, that is what makes it very difficult. Now, when I talked about, when I gave this example of sawing, you see that this task is only in 1D. It is only moving in the X direction. Okay, that means it is controlling everything only in the X direction, not in, this is not 3-dimensional. 3-dimensional is extremely complicated. Okay, so it is only doing this task in 1D, so it is sensing the force and it's moving the arm back in one dimension only, in one direction rather. Okay, now in this case, what we do is that you can imagine that the human is applying a force F, the robot is, there's a force torque, it has an FT sensor there, it's sensing the force and is moving back with a particular distance X. I need to find the relation between F and X now, because the human is applying a force, the robot is moving back. Okay, now if you look at the control structure of both these two systems, the robot is controlled using either Newton's law. Now what is Newton's law? Force is equal to mass into acceleration. What is the output input of this? I'm going to give a force and the output is what? Acceleration. So for a mass like this, if I give a force, what will happen is I'm going to get output as acceleration. This is basically called admittance. Okay, so when we are controlling the robot, the equation that I'm going to use is this equation: force is mass into acceleration. Okay, whereas in the case of the human, how is the human moving? The human has arms and the human has muscles. So when the human wants to move his hands, what the person would do is the muscle will contract. Okay, the muscle contracts here. The muscle contraction causes a force at the end effector. So there is a force here, and this is resulting in a force at the end effector or the arm. Okay, and that is how the force is coming. So what is the relation between the contraction of the muscle and the force? So the equation there is force is mass into acceleration plus c into x dot plus kx plus constant, let's call this k dashed. Okay, now if you see this equation and this equation are different, and this equation are different equations. Okay, this is called an impedance, this is called an impedance equation, this is called the admittance equation. Now you might say, so what? Okay. Now, so what is the question that we're trying to address here. So if the human is applying a force F, okay, the robot is measuring this force F. Let's say the human is applying 10 newtons. The robot is sensing 10 newtons. And the robot controller is this one. So it is saying 10 Newton is the force, mass into acceleration. It is integrating this equation twice and getting an x. It is getting, after integration, it is getting x. So it is moving back by an amount x. Okay. Whereas for the human was using this equation. Okay. And if you integrate this equation twice, this x will not be equal to this x. There will be a difference. Why? Because the equations are different now. So the amount the human has moved and the amount the robot has moved is different now. This fellow has moved x dashed and this fellow has moved x only. Now there's a mismatch. Okay, now I hope you understand what is the problem. Okay, so what will happen is either the task will fail or there will be some other problem. Okay. So such kind of controllers, what we do is basically we use an impedance control law. The robot also uses an impedance control law, and it is basically something like this, where we have a force sensor at the robot wrist. It measures the force which is given here, and this force is given to the impedance control equation. Here we are just using mx double dot plus cx. We are ignoring this term and this term is ignored. Okay, we are integrating this twice and getting x. Okay, so if I integrate this equation twice, I'll get x, and this x is given to the position controller and the robot moves back. Okay, so the challenge here being that I need to estimate what is m and what is c for the human. Okay, so m is the apparent mass and c is the damping. So I need to estimate that in the case of a human, and then put the values of m and c so that the robot can actually follow. That basically means the robot is behaving like a human. Okay, so this is another way of trying to explain how a robot can behave like a human. So these are the two concepts that we talked about today. One is impedance and the other is admittance. So in case of admittance, in case of impedance equation, so which we wrote as force is mass into acceleration plus cx dot plus kx plus k dashed. Okay, my input here is x is acceleration and the output is force. What is the input? This is the muscle acceleration, the muscle contraction, rather muscle contraction. And what is the output is force. So this is my impedance. What is admittance? Admittance is my input is force and the output is acceleration. And this is my Newton's law. Okay, this is called admittance. Okay, so one way of trying to find that m and c is you apply, say for example, we have two human beings perform a task. Okay, let me say there are two humans who are performing a task. Okay, let's say there is one human here and there is another human on the other side who is holding this object. Okay, so there is another human on this side. Okay, and there are force torque sensors which is applied onto the object. Okay, so one of the human is a leader and the other fellow is a follower. So this is a leader and he's a follower. The leader is forcing it in this direction or this direction, moving it. The follower is simply sensing the force and is moving and is following. You measure the force and the position of the object. So the force and position of the object is being measured. This is the force variation, this is the position variation. Now, once you have the relation between force and position, I basically want the parameters for this equation, mx double dot plus cx dot. Okay, so I can find what is m and what is c from these two graphs. And what we find is that m and c are not constants, but they vary, which is expected. So as m is with the velocity, when you're starting, m is very small. When you're ending the task, m is very large, because you need to accelerate and you need to decelerate. Okay, this is what it is showing, that force is increasing till the center, then it is decreasing. So the object is accelerating, then it is decelerating. Okay, so that's how we perform a task. So if I'm moving an object from here to here, I will accelerate, take it till there, and then stop it there. So we accelerate and then decelerate, and because of which the mass varies like this and the damping varies like this. Okay, so it depends on the velocity. So once we have that, we can design this controller which can actually behave like a human now. Okay, now these are called basic impedance control structures, in which the robot can actually behave like a human. Okay, now this is essentially fundamentally how robots interact with rigid environments, and the only way it can interact is it makes an assumption that F is equal to K into del X. Let us say there is a small deflection there, del X, and there is some K there. So by modifying this K, it behaves in a particular way. You can make the robot behave in a particular way. Okay, so for example, when there is contact in the motion, it has soft motion, so it uses very small value of K, a very low value of K. Whereas if there is, sorry, it's the other way around. So when contact is there, yeah. So when contact is there, for example, the human hand is hitting that wall. So what we do is basically we use soft motion control. So we have a less K. So when you're hitting against the wall, you'll make your hand soft. Why? Because you're absorbing the shock. Whereas if you're moving in free space, you can make it very stiff. You can have high K. Okay. So basically, high K or low K, or by changing the K, by varying the K value, we can make it stiffer or we can make it softer. Our hand can behave, or the motion control itself can be soft or it can be stiff. Okay, depending on whether you're hitting a hard environment or you're in a soft environment. And that is exactly what I had shown in the video I had shown, when the person is actually moving that link, that by simply changing the K, the link is behaving in a particular way. Okay, if the K is very high, so F is equal to K into del X, right? So if del X is equal to F by K, so it is F, the force being applied, by K. So if the force is the same, 10 newtons, if K is high, it's 10, then your del X is 1. Whereas in the other hand, if for the same force, if your K is very small, then your deflection is large. Okay, that's the meaning of high K or low K. Now, how do we design such controllers? Basically, this is one is we can have impedance control, we can have admittance control. This is my dynamic equation, which we have studied. Torque is equal to mass into acceleration plus Coriolis centrifugal forces, gravity plus other forces. Okay, so basically I can design a PD controller. This is my KP and this is my KD term, and this is the this term which is there. So if I take it and put it here, okay, what I'm going to get is I'll get this equation now. So what did I do? I took, this is the dynamics of the robot link. Okay, this is the desired dynamics. This is QD double dot. This is desired, the way it should behave. Okay, so this is my KP and my KD. So what I do is I take this equation, put it here, and what we get is this one. So this has KP and this is my KD, and this is mass into QD double dot minus Q double dot. Okay, now this one behaves like a PD controller. Now, so K and D, KP and KD have the dimensions of stiffness and damping. Okay, so they are commonly referred to as the stiffness and the damping matrix. So if I want the arm to behave in a particular way, I can change the values of KP and KD and make it behave in a particular way. Okay, as I just explained with the video in today's class, that if your KP is low, then it will be less stiff, and if your KP is high, then it is going to be very stiff. So I can simply make this robot behave in a particular way by playing with that KP and KD terms. This is an example, a robot in grinding task. So it is doing grinding. There is the grinding wheel there. So you can see the grinding wheel is grinding in a particular direction. So by simply changing that KP and KD, it is making it either having very soft kind of motion or very stiff kind of motion. This is another example. The robot is writing. So there's a pen with which the robot is writing. Maybe it has to write and draw this on the surface. Okay. So again, the robot has to press in this direction and has to move in that direction. Okay. So this is the robot writing on a surface. Okay. How can we make it behave in a particular way? How can we control its behavior? Can we make it stiff motion or can we make it soft motion? That is simply by changing these gains. Okay, and that is how we basically controlled robots in constrained tasks. Okay, so today we talked about force control in constrained tasks, and we saw that although it does appear that it's very easy to control robots for performing tasks, it is not so. And because of which you'll find that very often robots do very fundamental tasks, only pick and place, okay? But they don't do complex tasks like tightening a nut, tightening a screw, okay? Because it is extremely difficult to control forces in constrained tasks because there are so many variables that you have to control. And if you don't control accurately, the task will not get done, okay? That is something what humans are very good at and robots are very bad at. Now, in terms of force control, when we try and control the force that a robot is applying, the only way that we design such controllers is that we assume that there is some deflection and we say that there is a spring in between the robot and the constrained environment, and then we control the K of the spring. Okay, and that is how we talk about force control in constrained environments. So we'll stop here today and continue next class on multi-fingered robot hands. Thank you.